Hello and welcome to this short talk on MapleSim. MapleSim is a Maplesoft modeling and simulation package built on the symbolic computing engine of Maple. It's a system level simulation package, meaning that you could incorporate components from multiple different domains, whether they're from electrical, mechanical, thermal, hydraulics, and other specialist domains into one system level representation of the dynamics and the physics of a particular system. I have a completed model open up here of a robotic system. So what this robot looks like when we are before we simulate, we can visualize the robot itself and the geometry of this robot. We have certain contact points between the robot's head here and the ground, as well as the robot body. And internally there are some motors which are being used to drive the motion of this robot. So we have this 3D representation which we can use to interrogate or visualize our model. We have the traditional block diagram schematic representation, which is hierarchical and includes subsystems. So I can look inside these subsystems to see the different components which build this model. You can also see here that there are CAD geometries that help with the visualization and the incorporation of inertia from CAD files within this system. The model is also fully parameterized, so at a top level you can change various parameters. For example, this is a parameter for the radius of the wheel internally and the masses of the different parts of this mechanism. So when we simulate this model, here we are simulating for 20 seconds based on a certain initial condition. What MapleSim does is it goes off and uses the Maple engine to generate the mathematical equations which fully describe the dynamic behavior of this system. It then simplifies the mathematical equations down to a minimal set of equations prior to numerically integrating the system of equations and producing the result. We can see in the console output here that one of the key strengths of MapleSim is its ability to simplify the mathematical representation of the model down by using the Maple kernel. So the original system yields over 2,000 equations which are reduced down to a minimal set of 450 equations without any loss of accuracy or fidelity in the model. And here we see the simulation result. So in the simulation results window we can look at the various outputs from the probes, and we can also visualize the motion of this robot. So I'm going to go ahead and zoom in a bit so that you can see that, and I will select the robot body and then hit the animation button, and we can see the dynamic behavior that we have simulated in this particular model based on these initial conditions. So by applying these symbolic routines, we are improving the efficiency of the simulation. So if you wanted to take this into a real-time system or perform optimization of parameters, for that kind of thing, this process yields very efficient code. So right now I'm going to build a simple model to show you what the workflow is to build the system level model. Now, another key strength of MapleSim is its ease of use. It's been designed from the beginning to be a physical modeling tool, so everything is should be easier to use for that particular purpose. So I'll start with an empty canvas, empty worksheet. I have a visualization of what I'm building here. I'll also increase the base radius of the generated geometry. The base radius is, if I just show you by dragging on a block, this is just a link in space. The base radius, sorry, if I increase this to 0.1, means that the geometry increases in size and we can see it a bit better. It doesn't actually affect the dynamics, that is defined by other components. So this rigid body frame is a displacement in space. I can drag on a rigid body component. This has a particular mass and inertia matrix. You can see here on the right hand side of the window, I see the parameters for this particular component, and you can also see that there are units associated with these parameters. So here it's saying this rigid body has a mass of 1 kilogram, and this is its inertia matrix, rotational inertia, as well as the initial conditions for this particular rigid body. Now, if I connect this rigid body to the end of this link, you can see that the 3D window has updated. Now, the left-hand side of this rigid body frame is not connected to anything, so it's floating in space. What we can do is we can bring in a fixed frame, and we can attach the rigid body frame to this fixed frame via a rotational joint. So in my joints and motions, I have a revolute joint here. You can drag that onto the workspace and connect up this joint to my fixed frame, and then connect the outboard frame of this revolute joint, which is the frame that is in motion, to this rigid body frame. So now I have built a very simple mechanical system of a pendulum type of mechanism here. There are no torques currently driving this joint. So under the force of gravity on this rigid body, we should get a motion backwards and forwards around this revolute joint. And there's also no friction in the model currently defined. So I can probe for a mechanical quantity here of phi, which is the angle, speed, and acceleration, phi, w, and a. So that should be my output from this joint. If I hit simulate now with the default initial conditions, this will simulate for 10 seconds. So as you can see, it's very quick. So I have the simulation result already generated for me here. I could look at this simulation result like so, and I see the 3D view and also the 2D view here, and I can see this pendulum swinging backwards and forwards. I also see the trace of which location it is in the 2D view in my animation. So as you can see, it's a very simple dynamic that we have modeled here. Going back into my 2D view, if I copy and paste these components and add a secondary rigid body frame to the end of this first rigid body, now I have changed the architecture of this system. So now you can see that there is a second rigid body on the end and a second revolute at the end of this first link. So by changing the architecture, I have changed the dynamics, and we've also copied the probe, so we have a secondary probe output. Simulating again, we can see the subsequent change in the dynamic behavior. So we now have a double pendulum swinging backwards and forwards. Let's go back into the model. Now, one unique aspect of this approach is that we could interrogate this model from Maple. Maple is used under the hood to generate the mathematical equations from the model. So if I wanted to generate the mathematical equations, let's say from just the one link system, I'll temporarily disable the second link. I can step into Maple. So the relationship between MapleSim and Maple is very close. There are templates for doing various things here, and apps as well. Apps are non-editable by the user. Templates are editable by the user. So there's, for example, apps to take this model into Simulink. I will open an empty worksheet, an empty Maple worksheet, to show you from first principles what is involved in creating an interaction between the model and the Maple analytical environment. So you can see here, this is MapleSim. I've now stepped into Maple. If you want an introduction to Maple, you can take a look at the other talk. But the Maple environment is a document environment. Here we have a MapleSim component, which is essentially a link between the MapleSim model and Maple. And I have a programming interface here to interact with my model. So I can associate this particular model with a variable. I can call this my model. When I execute that, now I have a reference called my model to interrogate this particular model with. So this name, once I executed this command, allows me to query the model. For example, if I want the multibody equations from this this model, I can issue the get multibody command. This is a input just to tell it to simplify as much as possible the result. When I execute this, I get an analysis of the system. Here it's saying that it has 1 degree of freedom. It can rotate in 1 rotational degree, and this is the variable that it has chosen as its rotational degree of freedom. I can attach this multibody analysis to another name. I'll call it MB, and then I can extract the dynamic equations from this model by issuing this secondary command called getDinEQs. So by default, all the parameters are substituted into the expressions when they are returned. But if I step back into the model here, I can add some top-level parameters. For example, the mass of this primary link. So I'll call that M1, and I'll change the IZZ value to a symbolic IZZ, and I'll change this length to be L over 2. Likewise for the second rigid body frame, I'll do L over 2. So this center of mass is located in between these two links, and the length of this link is now defined by the parameter L. And we can define these at a top level in a parameter block. So I'll define M1 as my mass of link and L as length of link. Likewise, I define IZZ, And if I want the gravitational acceleration to appear in my equation, I might want to add another parameter for g, 9.81. Finally, I change the gravitational acceleration from 9.81 in the simulation settings to the symbolic parameter g, which I have defined in my parameter block here. So now I have 4 parameters in my model, which I have defined myself. If I step back into my Maple analysis and regenerate the analysis, we can see that the equations are updated accordingly. Going back into the model and re-enabling the secondary link, now I have changed the topology of the model, and the analysis sheet will reflect that change by re-executing the worksheet. So here I see the equations which describe the 2-link pendulum, and you can see here that now it has 2 degrees of freedom modeled by 2 generalized coordinates. So once these expressions are within Maple, you have all of the functionality of Maple to perform advanced analysis on your system level model. And that's one of the unique features of MapleSim. We could, so if I close this worksheet now, this worksheet is saved within the model itself. So I have that in my attached files. We could also generate a new component from equations. And that's another feature of this approach, that I could define a custom component based on equations. So if I go back into my templates and open a custom component template, I'll define this as an angle stop. This will be a contact element on my Revolute. So this again opens up Maple. This time the template looks a little different because it has a different function. So in this template I specify an equation which describes my component. When I open the template, there is a default example which is I think a DC motor. I'll get rid of this equation and I can define my own equation for this particular component. So what I will define is a torque, which is a function of time, which is equal to a piecewise function. So this will be dependent on a particular input. There'll be a constant damping for the contact torque, and this will be multiplied by the first derivative with respect to time of the angle, which is defined by theta t, plus another constant multiplied by theta of t. And this torque will be applied at a particular value of theta of t. So the condition on this piecewise function is if theta of t, let's say, for example, is less than or equal to a particular angle, and 0 otherwise. Once I hit enter, we can see here it has returned the result in blue, meaning that Maple has now understood what you mean as this expression here. Next, we need to define the ports for this component. Now I can refresh these parameters, and I can see angle, C, and K appear as parameters because they're non-time variant. And variables, if I refresh those, I can see theta and tau appear as my 2 variables for this component based on how I have defined my equation. Finally, I define the ports. I'll clear all the default the ports from the example and add a single port which will be a rotational flange. So it's a rotational mechanical port. In this modeling paradigm, the acausal modeling paradigm, we have 2 variables which we need to define, which are the angle and torque of this particular rotational mechanical joint, this rotational mechanical port. And the angle will be defined from my equation as theta of t, and the torque will be defined as tau of t. I will give this component a name. I'll call this angle stop. And finally, I can generate this component into my model. It then appears in my local components. I can drag that onto the workspace, and I can go ahead and attach it to my model. In this case, let me attach it to the first revolute joint. So what this architecture shows is that whatever the angle of this joint, if it is less than or equal to this parameter that I have defined, angle, I'll change that to negative pi over 4, for example, at 45 degrees from the horizontal. If this angle is less than this, we will apply the torque that we defined in the equation. So I'll change these parameters to slightly higher values so we can see a sharper response. So now I have defined my model. If I rerun the simulation, so here we see the corresponding contact. So as this angle phi 1 reaches this value, we see the contact happening, and we can actually see that in the 3D animation as well. Let me switch that to the front perspective, and you can see that a bit better. Finally, I will show you how to generate this model into code or Simulink or functional mockup interface to take it externally to MapleSim. To do that, I wrap this in a subsystem. I'll call this sys, something like that. So all of my components are now within this subsystem. I can define an output to this subsystem. I can define both inputs and outputs, but let's just define an output for simplicity by attaching a sensor. So if I attach an angle sensor to this particular joint, this angle sensor will convert this angle into a signal, which will be my output, and I can attach that to the output port here and give this a name. So now my subsystem has one output defined, as you can see here. So in a similar way to how we use the templates, there are apps which allow me to perform certain tasks. So the code generation app is the most generic form of output. We can generate C code, which is standalone and royalty free. They can run standalone in any external code. There is also a Simulink component block generation app, which is a variation of the code generation app, which generates the Simulink S function. So to show you what this app looks like, if I open the app, we can see it opens up in the analysis window, and I can now see the model within this app, allowing me to select the subsystem that I want to generate the S function or C code from, and I can load this selected subsystem into the app. Okay, so there is a slight issue here with the parameter block, so I need to just take that externally. So everything looks okay now. So if we step back into the app and reload the selected subsystem, I can see that it has not given me any errors, so everything is fine. It has detected that I have 0 inputs in this case. It should have detected, yes, 1 output by the fact that I have a port defined in my subsystem. It has detected the various parameters, the ones that I have defined here. And if I wanted to, I can export other parameters in this code. So the code will be fully parameterized. And then there's code export options as well that I can select. And finally, I generate the code. When I click that, I get the block generation script here. This is what needs to be run in order to generate the block. And I also get the C code, which describes the model in question. It's not recommended to edit this by hand, but there is documentation for the interface functions within this code. Okay, so this is a very short introduction to the capabilities of MapleSim. I hope you found it useful. Thank you very much for your time.